2.5 Ideal and non-ideal solutions. Liquid to liquid solutions can be classified into ideal and non-ideal solutions on the basis of the Raoult's law. 2.5.1 Ideal solutions. The solutions which obey Raoult's law over the entire range of concentrations are known as ideal solutions. The ideal solution have two other important properties. The enthalpy of mixing of the pure components to form the solution is 0 and the volume of the mixture is also 0, that is given in 2.21. It means that no heat is absorbed or evolved when the components are mixed. Also, the volume of the solution would be equal to the sum of the volume of the two components. At the molecular level, ideal behavior of the solutions can be explained by considering two components A and B. In pure components, the intermolecular attractive interactions will be of two types, A to A and B to B, whereas in the binary solution, in addition to these two interactions, A to B type of interaction will also be present. If the intermolecular attractive forces between the A to A and B to B are nearly equal to those between the A to B, this led to the formation of the ideal solution. A perfectly ideal solution is rare, but some solutions are nearly ideal in behavior. Solution of N-hexane and N-heptane, bromoethane and chloroethane, benzene and toluene, etc. fall into this category. 2.5.2 Ideal non-ideal solution. When a solution does not obey Raoult's law over the entire range of concentration, then it is called as the non-ideal solution. The vapor pressure of such a solution is either higher or lower than the predicted by the Raoult's law. Equation 2.16. If it is higher, the solution exhibits positive deviation, and if it is lower, it exhibits negative deviation from the Raoult's law. The plots of vapor pressure as a function of mole fractions for such solutions are shown in figure 2.6. The causes for these deviations lie in the nature of interactions at the molecular level. In the case of positive deviation from the Raoult's law, A to B interactions are weaker than those between A to A and B to B interactions. That is, in this case, the intermolecular attractive forces between the solute-solvent molecules are weaker than those of between the solute-to-solute and solvent-to-solvent molecules. This means that in such solutions, molecules A or B will find it easier to escape than in the pure state. This will increase the vapor pressure and result in the positive deviation. Mixtures of ethanol and acetone behave in this manner. In pure ethanol, molecules are hydrogen bonded. On adding acetone, its molecules get in between the host molecules and the interactions. The solutions molecules and break some of the hydrogen bonds between them. Due to weakening of the interaction, the solution shows positive deviation from the Raoult's law. Figure 2.6a. Figure 2.6 shows the vapor pressure of the two component systems as a function of composition. A solution that shows positive deviation from Raoult's law, and B, a solution that shows negative deviation from Raoult's law. In a solution formed by adding carbon disulfide to the weaker acetone, the dipolar interaction between the solute to solvent molecules are weaker than the respective interactions among the solute to solute and solvent to solvent molecules. These solutions also shows positive deviations. In case of negative deviation from the Raoult's law, the intermolecular attractive forces between A to A and B to B are weaker than those between the A to B and leads to the decrease in the vapor pressure, resulting in the negative deviation. An example of this type is the mixture of phenol and aniline. In this case, the intermolecular hydrogen bonding between the phenolic proton and lone pair on nitrogen atom of aniline is stronger than the respective intermolecular hydrogen bonding between the similar molecules. Similarly, a mixture of chloroform and acetones form a solution with negative deviation from Raoult's law. This is because chloroform molecule is able to form hydrogen bond with the acetone molecule as shown. This decreases the escaping tendency of the molecules for each component, and consequently the vapor pressure decreases, resulting in a negative deviation from the Raoult's law. Figure 2.6b. Some liquids on mixing from the azeotrophs, which are binary mixtures having the same composition in liquid and vapor phase, and they boil at the constant temperature. In such cases, it is not possible to separate the components by fractional distillation. There are two types of azeotrophs called the minimum boiling azeotrophs and the maximum boiling azeotrophs. The solutions which show a large positive deviation from the Raoult's law form minimum boiling azeotrophs at a specific composition. For example, ethanol water mixture obtained by fermentation of sugars on fractional distillation gives a solution containing approximately 95% by volume of ethanol. Once this composition, known as azeotrophs composition, has been achieved, the liquid and the vapor have the same composition and no further separation occurs. The solutions that shows large negative deviation from the Raoult's law form maximum boiling azeotrophs at a specific composition. Nitric acid and water is an example of this class of azeotrophs. This azeotroph has the approximate composition 68% nitric acid and 32% water by mass, with a boiling point of 393.5 Kelvin. 2.6 Colligative properties and the determination of the molar mass. We have learnt in section 2.4.3 that the vapor pressure of the solution decreases when a non-volatile solute is added to a volatile solvent. There are many properties of the solutions which are connected with this pressure of the solvent. These are 1. Relative lowering of the vapor pressure of the solvent, 2. Depression of the freezing point of the solvent, 3. Elevation of the boiling point of the solvent, and 4. Osmotic pressure of the solution. All these properties depend on the number of the solute particles irrespective of their nature relative to the total number of particles present in the solution. Such properties are called colligative properties. Colligative from Latin co means together and ligare means to bind. In the following sections we will discuss this property one by one. 2.6.1 Relative lowering of the vapor pressure. We have learnt in section 2.4.3 that the vapor pressure of a solvent in a solution is less than that of the pure solvent. Raoult's law established that the lowering of the vapor pressure depends only on the concentrations of the solute particles and it is independent of their identity. The solution equation 2.20 given in section 2.43 establishes a relation between vapor pressure of the solution, mole fraction, and the vapor pressure of the solvent, that is P1 is equal to x1 P1 naught. 2.22 The reduction of the vapor pressure of the solvent del P1 is given as del P1 is equal to P1 naught minus P1 is equal to P1 naught minus P1 naught x1 is equal to P1 naught 1 minus x1. 2.23 Knowing that x2 is equal to 1 minus x1, equation 2.23 reduces to del P1 is equal to x2 P1 naught Equation 2.24. In a solution containing several non-volatile solutes, the lowering of the vapor pressure depends on the sum of the mole fraction of different solutes. Equation 2.24 can be written as del P1 by P naught 1 is equal to P naught 1 minus P1 by P naught 1 is equal to x2. 2.25. The expression on the left hand side of the equation, as mentioned earlier, is called the relative lowering of the vapor pressure and is equal to the mole fraction of the solute. The above equation can be written as P naught 1 minus P1 by P naught 1 is equal to N2 by N1 plus N2, since x2 is equal to N2 by N1 plus N2. Equation 2.26. Here N1 and N2 are the number of the moles of the solvent and solute respectively present in the solution. For dilute solution, N2 is much lesser than N1. Hence, neglecting the N2 in the denominator, we have P naught 1 minus P1 by P naught 1 is equal to N2 by N1, or P naught 1 minus P1 by P naught 1 is equal to W2 into M2 by M2 into W1. Here W1 into W2 are the masses and the M1 and M2 are the molar masses of the solvent and solute respectively. From this equation 2.28, knowing all the other quantities, the molar mass of the solute M2 can be calculated. Example 2.6 is given in your textbook. Please read that. 2.6.2 Elevation of the boiling point. We have learnt in Unit 5, Class 11 that the vapor pressure of the liquid increases with the increase of temperature. It boils at the temperature at which its vapor pressure is equal to the atmospheric pressure. For example, water boils at 373.15 Kelvin, 100 degrees Celsius, because at this temperature the vapor pressure of the water is 1.013 bar, 1 atmosphere. We have also learnt in the last section that vapor pressure of the solvent decreases in the presence of the non-volatile solute. Figure 2.7 depicts the variation of the vapor pressure of the pure solvent and solution as a function of the temperature. For example, the vapor pressure of an aqueous solution of sucrose is less than 1.013 bar at 373.15 Kelvin. In order to make this solution boil, this vapor pressure must be increased to 1.013 bar by raising the temperature above the boiling point of the pure solvent water. Thus, the boiling point of the solution is always higher than that of the boiling point of the pure solvent in which the solution is prepared, is shown in figure 2.7. 2.7 figure shows that the vapor pressure curve for the solution lies below the curve for pure water. The diagram shows that del Tb denotes the elevation of the boiling point of a solvent in a solution. Similar to lowering of the vapor pressure, the elevation of the boiling point also depends on the number of the solute molecules rather than their nature. A solution of 1 mole of sucrose in 1000 gram of water boils at 373.52 Kelvin at 1 atmospheric pressure. Let Tb not be the boiling point of the pure solvent and Tb be the boiling point of the solution. The increase in the boiling point del Tb equals to Tb minus Tb naught is known as the elevation of the boiling point. Experiments have shown that for a dilute solution, the elevation of the boiling point del Tb is directly proportional to the molar concentration of the solute in the solution. Thus, del Tb is directly proportional to the m, equation 2.29, or del Tb is equal to kbm, equation 2.30. Here m, molality, is the number of moles of solute dissolved in 1 kg of solvent, and the constant of proportionality kb is called the boiling point elevation constant or molar elevation constant or ebullioscopic constant. The unit of kb is kg per mole. Values of the kb of for some common solvents are given in table 2.3. If W2 gram of solute of molar mass M2 is dissolved in the W1 gram of solvent, then the molality M of the solution is given by the expression M equals to W2 by M2 by W1 by 1000 equals to 1000 into W2 by M2 into W1, equation 2.31. Substituting the value of the molality in the equation 2.30, we get del Tb equals to Kb into 1000 into W2 by M2 into W1, 2.32. M2 is equal to 1000 into W2 into Kb by del Tb into W1, equation 2.33. Thus, in order to determine M2 molar mass of the solute, known mass of the solute is known mass of the solvent is taken and del Tb is determined experimentally for a known solvent whose Kb value is known. Example 2.7 is given in your textbook. Please read, and example 2.8 is also given in your book. 2.6.3 Depression of freezing point. The lowering of the vapor pressure of a solution causes a lowering of the freezing point compared to that of the pure solvent. Figure 2.8. We know that at the freezing point of the solute substance, the solid phase is in dynamic equilibrium with the liquid phase. Thus, the freezing point of a substance may be defined as the temperature at which the vapor pressure of the substance in its liquid phase is equal to the vapor pressure in its solid phase. A solution will freeze when its vapor pressure equals the vapor pressure of the pure solid solvent, as in the clear form figure 2.8. According to Raoult's law, when a non-volatile solid is added to the solvent, its vapor pressure decreases, and now it would become equal to that of the solid solvent at lower temperature. Thus, the freezing point of the solvent decreases. Let Tf naught be the freezing point of the pure solvent and Tf be the freezing points when non-volatile solute is dissolved in it. The decrease in the freezing point del Tf is equal to Tf naught minus Tf is known as the depression in the freezing point. Similar to the elevation of the boiling point, depression of the freezing point del Tf for a dilute solution, ideal solution, is directly proportional to the molality M and the solution. Thus, del Tf is directly proportional to M and or del Tf equals to Kfm, equation 2.34. The proportionality constant Kf, which depends on the nature of the solvent, is known as freezing point depression constant or molar depression constant or cryoscopic constant. The unit of Kf is kg per mole. Values of Kf for some common solvents are listed in table 2.3. If W2 gram of the solute having molar mass as M2 present in the W1 gram of the solvent produces the depression in the freezing point del Tf of the solvent, then the molality of the solute is given by the equation 2.31. M is equal to W2 by M2 by W1 by 1000, 2.31. Substituting this value of molality in equation 2.34, we get del Tf is equal to Kf into W2 by M2 by W1 by 1000. Del Tf equals to Kf into W2 into 1000 by M2 into W1, equation 2.35. M2 equals to Kf into W2 into 1000 by del Tf into W1, equation 2.36. Thus, for determining the molar mass of the solute, we should know the quantities W1, W2, del Tf along with the molar freezing point depression constant. The values of Kf and Kb, which depends upon the nature of the solvent, can be ascertained from the following relation. Kf equals to R into M1 into Tf square by 1000 into del enthalpy of fusion. Kb equals to R into M1 into Tb square by 1000 into del enthalpy of vaporization. 2.38. Here the symbols R and M1 stand for the gas constant and the molar mass of the solvent respectively, and the Tf and Tb denote the freezing point and the boiling point of the pure solvent respectively in Kelvin. Further, del enthalpy of fusion and enthalpy of vaporization represent the enthalpies for the fusion and vaporization of the solvent respectively. Table 2.3 shows the molar boiling point elevation and freezing point depression constant for some solvents. Example 2.9 is given and example 2.10 is also given in your textbook. Please read from the book. Then 2.6.4, osmosis and osmotic pressure. There are many phenomena which we observe in the nature or at home. For example, raw mangoes shrivel when pickled in brine salt water, beetle flower revive when placed in fresh water, blood cell collapse when they suspended in saline water, etc. If we look into these processes, we find one thing common in all, that is, all these substances are bound by the membranes. These membranes can be of animals or vegetable origin, and this occurs naturally, such as pig bladders, or parchment, or can be synthetic, such as cellophane. These membranes appear to be continuous sheet or films, yet they contain a network of the submicroscopic holes or pores. Figure 2.9 shows the level of the solution rise in the threshold funnel due to the osmosis of solvent. Small solvent molecules like water can pass through these holes, but the passage of bigger molecules like solute is hindered. Membranes which having this kind of properties are known as the semi-permeable membranes, in short SPM. Assume that only solvent molecules can pass through this semi-permeable membrane. If this membrane is placed between the solvent and the solution as shown in figure 2.9, the solvent molecules will follow or flow through the membrane through pure solvent to the solution. This process of flow of the solvent is called as the osmosis. The flow will till the equilibrium is attained. The flow of the solvent from its side to the solution side across a semi-permeable membrane can be stopped if some extra pressure is applied to the solution. This pressure that stops the flow of the solvent is called the osmotic pressure of the solution. The flow of the solvent from dilute solution to the concentrated solution across a semi-permeable membrane is due to the osmosis. The important point to be kept in mind is that the solvent molecules always flow from the lower concentration to the higher concentration of the solution. The osmotic pressure has been found to depend on the concentration of the solution. The osmotic pressure of a solution is the excess pressure that must be applied to a solution to prevent osmosis, that is, to stop the passage of solvent molecules through a semi-permeable membrane into the solution. This is illustrated in figure 2.10. Osmotic pressure is a colligative property as it depends on the number of the solute molecules and not on their identity. For dilute solutions, it has been found experimentally that osmotic pressure is proportional to the molarity C of the solution at a given temperature T. Thus, pi is equal to CRT. Here, pi is the osmotic pressure and R is the gas constant. Pi is equal to N2 by VRT. Here, V is the volume of a solution in liters containing N2 moles of solute. If W2 grams of solute of molar mass M2 is present in the solution, then N2 is equal to W2 by M2, and we can write pi V is equal to W2 into RT by M2, or M2 equals to W2 RT by pi V. Thus, knowing the quantities W2, T, pi and V, we can calculate the molar mass of the solute. Measurement of the osmotic pressure provides another method of determining the molar masses of the solutes. This method is widely used to determine molar masses of proteins, polymers, and other macromolecules. The osmotic pressure method has the advantage over other method as pressure measurement is around the room temperature and the molarity of the solution is used instead of molality. As compared to the other colligative properties, its magnitude is large even for very dilute solution. The techniques of osmotic pressure for determination of the molar mass of the solute is partially useful for the biomolecules as they are generally not stable at higher temperatures and polymers have poor solubility. Two solutions having same osmotic pressure at a given temperature are called the isotonic solutions. When such solutions are separated by the semi-permeable membrane, no osmosis occurs between them. For example, osmotic pressure associated with the fluid inside the blood cell is equivalent to that of the 0.9% mass by volume sodium chloride solution called the normal saline solution, and it is safe to inject intravenously. On the other hand, if we place the cell in a solution containing more than 0.9% mass by volume sodium chloride, water will flow out of the cell and they would shrink. Such a solution is called hypertonic. If the solution salt concentration is less than 0.9% mass by volume, the solution is said to be hypotonic. In this case, water will flow into the cell if placed in this solution and they would swell. Example 2.11 is given in your book. Please read. The phenomena mentioned in the beginning of this section can be explained on the basis of osmosis. A raw mango placed in the concentrated salt solution loses water via osmosis and shrivel into prickle. Beetle flowers revive when placed in the fresh water. A carrot that has become limp because of the water loss into the atmosphere can be placed into the water, making it firm once again. Water will move into its cells through osmosis when placed in water containing less than 0.9% mass by volume salt. Blood cells swells due to flow of water in them by osmosis. People taking a lot of water or salty food experience water retention in the tissue cells and intracellular spaces because of osmosis. The resulting puffiness and swelling is called the edema. Water movement from the soil into the plant roots and subsequently into the upper portion of the plant is partly due to the osmosis. The preservation of meat by salting and of fruits by adding sugar protects against the bacterial actions through the process of osmosis. A bacterium on salted meat or candied fruits loses water, shrivells and dies. 2.6.5 Reverse osmosis and water purification. The direction of osmosis can be reversed if a pressure larger than the osmotic pressure is applied to the solution side. That is, now the pure solvent flows out of the solution through the semi-permeable membrane. This phenomenon is called the reverse osmosis and is of great practical utility. Reverse osmosis is used in the desalination of the seawater. A schematic set up for the process is shown in figure 2.11. When pressure more than the osmotic pressure is applied, pure water is squeezed out of the seawater through the membrane. A variety of polymer membranes are available for this purpose. The pressure required for the reverse osmosis is quite high. A workable porous membrane is a film of cellulose acetate placed over a suitable support. Cellulose acetate is permeable to water but impermeable to impurities and ions present in the seawater. These days, many countries use desalination plants to meet their potable water requirements. Figure 2.11 shows the reverse osmosis occurs when a pressure larger than the osmotic pressure is applied to the solution. Then 2.7 Abnormal molar masses. We know that the ionic compounds, when dissolved in water, dissociate into cations and anions. For example, if we dissolve 1 mole of KCl 74.5 gram in water, we expect 1 mole each of K plus and Cl minus ions to be released in the solution. If this happens, there would be 2 moles of the particles in the solution. If we ignore the interionic attractions, 1 mole of KCl in the solution, 1 kg of water would be expected to increase the boiling point by 2 into 0.25 Kelvin equals to 1.04 Kelvin. Now, if we did not know about the degree of dissociation, we could be led to conclude that the mass of 2 mole particles is 74.5 gram and the mass of 1 mole of KCl would be 37.25 gram. This brings into light that the rule that when there is dissociation of solute into the ions, the experimentally determined molar masses is always lower than the true value. Molecules of ethanoic acid, acetic acid dimerize in benzene due to the hydrogen bonding. This normally happens in the solvent of low dielectric constant. In this case, the number of particles is reduced due to the dimerization. Association of molecules is depicted as follows. It can be undoubtedly stated here that if all the molecules of ethanoic acid associate in the benzene, then del Tb or del Tf for the ethanoic acid will be half of the normal value. The molar mass calculated on the basis of this del Tb or del Tf will therefore be twice the expected value. Such a molar mass has that the either lower or higher than expected or normal value is called as the abnormal molar mass. In 1880, Van Zoff introduced a factor I, known as the Van Zoff factor, to account for the extent of the dissociation or association. This factor I is defined as I equals to normal molar mass by abnormal molar mass equals to observed colligative properties by calculated colligative properties. I equals to total number of moles of the particles after association or dissociation by number of moles of the particles before association or dissociation. Here, abnormal molar masses is the experimentally determined molar mass, and calculated colligative properties are obtained by assuming that the non-volatile solute is either associated not dissociated. In case of association, value of I is less than unity, while for the dissociation it is greater than unity. For example, the value of I for the aqueous KCl solution is close to 2, while the value of the ethanoic acid in benzene is nearly 0.5. Inclusion of Van Zoff factor modifies the equation for the colligative properties as follows. Relative lowering of the vapor pressure of the solvent, P01 minus P1 by P01 equals to I into N2 by N1. Elevation of the boiling point, del Tb equals to I into Kbm. Depression of the freezing point, del Tf equals to I into Kfm. Osmotic pressure of the solution, pi is equal to I into N2RT by V. Table 2.4 depicts value of the factor I for several strong electrolytes for KCl, NaCl and MgSO4. I values approach 2 as the solution becomes very dilute. As expected, the value of I gets close to 3 for K2SO4. Example 2.12 and 2.13 is given in your textbook. Please read that. Summary. A solution is a homogeneous mixture of two or more substances. Solutions are classified as solid, liquid, and gaseous solutions. The concentration of a solution is expressed in terms of the mole fraction, molarity, molality, and in percentages. The dilution of a gas in a liquid is governed by Henry's law, according to which at a given temperature the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas. The vapor pressure of the solvent is lowered by the presence of a non-volatile solute in the solution, and this lowering of the vapor pressure of the solvent is governed by the Raoult's law, according to which the relative lowering of the vapor pressure of the solvent over a solution is equal to the mole fraction of a non-volatile solute present in the solution. However, in a binary liquid solution, if both the components of the solutions are volatile, then the another form of Raoult's law is used. Mathematically, this form of the Raoult's law is stated as P total is equal to P naught 1 x1 plus P 2 naught x2. Solutions which obey Raoult's law over the entire range of concentrations are called the ideal solution. The two types of deviations from the Raoult's law, called the positive and negative deviations, are observed. Azeotrophs arises due to the very large deviation from the Raoult's law. The properties of the solutions, which depends on the number of solute particles and are independent of their chemical identity, and are called colligative properties. These points and osmotic pressure. The process of osmosis can be reversed. If pressure higher than the osmotic pressure is applied to the solution, colligative properties have been used to determine the molar mass of solutes. Solutes which dissociate into the solution exhibit molar mass lower than the actual molar mass, and those which associate show higher molar mass than their actual values. Quantitatively, the extent to which a solute is dissociated or associated can be expressed by Van 't Hoff factor I. This factor has been defined as the ratio of normal molar mass to experimentally determined molar mass, or as the ratio of observed colligative property to the calculated colligative properties. Thank you.